Hello everyone, my name is Maz Barami from Wolfram Research. Welcome to the second session of our live coding series with Anton Antonov. If you join us for the first time, Anton has a PhD degree in applied mathematics from the Technical University of Denmark, and he has been using Wolfram technology for more than 20 years. As an applied mathematician, Anton has worked in algorithm development, mathematical modeling, natural language processing, optimization, data mining, and machine learning. Today will be the second part of live coding series on quantile regression workflow. Without further ado, let us welcome our instructor, Anton Antonov.
Thank you, Matt, for the introduction. All right, so today we're going to have a follow-up of what we discussed last time. And so I'm going to briefly mention what we discussed last time. So we're looking into quantile regression pipelines. Basically, this is a simple quantile regression pipeline. What you see here, I have taken some distribution data, which is being shown here with these gray points, and I have made a regression fit. Roughly speaking, I have fit some curves into it. This here it's a standard linear regression fit, and you can see both of them are being compared. I can do some other stuff here, like for example, if I don't specify the quantiles, then the probabilities, then the default probabilities, 25%, 50%, 75% are being fit. So why I'm using this, and why I'm using this structuring kit in a pipeline? Well, here's my end game is basically this. Trying to produce some sort of simple conversational agents or conversational natural command interpreters which produce these pipelines. If I execute this, if I evaluate in place what this pipeline was, this natural language command, you see it translates into this monadic expression. This is one of the advantages of using monads. Your code has algebraic structures. Because of this algebraic structure, I can do stuff like this. I can make this kind of translations. I mean, this is happening in real time. I don't need to unfold it. But basically, this is exactly what this function is doing. It's producing a fragment of the monadic pipeline. That fragment is being plugged into a bigger pipeline, and then the whole thing works. All right, I'm not going to expand more on this, but this is the reason I'm using the monadic pipelines. Because of some things going, for the plans I have for utilizing that kind of functionality. The monads were basically a user interface to this kind of functionalities, which can be fairly complex. So we saw here actually the comparison with my first example with least squares. Last time I was also discussing comparison with neural networks, and I was showing how to find outliers. So here, in this pipeline, we're finding outliers in the distribution data by using two probabilities. I'm going to expand a little bit on that. So this is, I'm sharing the notebook. This is how we can load the packages. The packages on GitHub. All right, so briefly, I'm going to mention the data we're going to use. We have the distribution data, which I already used, weather data from Orlando temperature from 2015 to 2019. Some financial data. I use this financial data example from Mathematica help and browser, and it will be clear why we're going to show that. And the last is the data that we're going to be cleaned. To show a cleaning example, and actually I think that's the best way to start. So I'm going to do a monad with that sample data, and actually at this point I'll just do a plot. All right, and so the idea is that we have this kind of data here, right? So we have a point. Can we clean that point? And there are several ways to do that. So I'm going to iteratively build up in this pipeline and trying to make the cleanup, right? So first I'm going to fit quantile regression, make a quantile regression fit, right? Say I usually use 12 nodes, 12 knots. So with this particular data, actually, let me think a little bit. That's not it's not exactly what I expected. And let me try to remedy the situation with a more complicated method. So by default, I use a library called CLP, which is an open source library which linear programming uses. And interior point is an internal implementation by Wolfram Research about linear programming. The CLP in general is faster, but in some cases, and you see there's some kind of slightly pathological case here. If you look at the spans in the x-axis and y-axis, it is better in some cases. It's better to be able to switch the methods. All right. So what I'm going to do next is I'm going to plot the errors. And the errors here, just a moment, error plots. I can do two types of errors, right? I can do relative errors and I can do absolute errors. I want to use the absolute errors. It become clear why. And so here is, oh, sorry, I should have put the plotting of the fit and the data before that. All right, so now it should be kind of clear, right? I mean, if you look at this this data here, and there are plots. So, I mean, I can clearly see that there is a decisive outlier, although the actual value, you know, yeah, I mean, it can be quite big. And I can, you know, I basically will have this this code fragment here. I'm going to copy and paste, which is just going to show how the clean data is being produced. Okay, well, I forgot to make an assignment here. So, all right. So when we do monadic programming, we go into the monad, and then we need to get out of the monad. So I'm going to take this here. I'm getting out of the monad with this take value, and with clean data is going to be assigned this value I took. And I strongly suspect that I'm missing a step here. All right. Well, it wasn't enough just to find the errors, right? I need to also try to pick the points which are close to this close enough to the curve which I just fitted. So as I said, I'm missing a step here. All right, and so I'm going to do that here. I'm going to do QMon path points. From looking at the errors here, the threshold I'm going to use, it can be something like, say, this. And now I really hope, well, we have much better results. All right, so here, what happened? I made a quantile regression with a certain number of nodes. I had to fiddle with the method, and for linear programming, I did look into the errors of basically how far these points from the original data are from the curve which was fitted. And looking at the errors, I specify that I want to pick only the points which are below this threshold. And this is obviously absolute. So I want to pick points which are close to the curve. This means that this point is going to be isolated. And this is exactly what happened here. The clean data, it does not have, I mean, we can see the original sample data is this pink large disks, not points anymore. And the blue points is the clean data. And you can see what we don't have it. It has been cleaned. All right, so why I'm showing this? Well, because this actually can be convenient to do residual outliers. And I'm going to discuss the contextual outliers, which we already kind of did. So I'm going to jump immediately from this example to residual outliers. So basically, what we have with the residual outliers, or what is the why I'm talking residual outliers? What does this mean? We have two types of outliers, many, but let's say, roughly speaking, what we are going to consider here is outliers by context, right? So something like here, this is not this point here, it's not an absolute outlier, but it can be seen an outlier in the vicinity of this point. Same with this one. It's not an absolute outlier here in the y-axis, but it can be seen as an outlier in the context here around this area. So this is a contextual outlier, but we can also have, of course, point outliers, and this is point anomalies, and this is a point anomaly which we cleaned up. So I actually wanted to kind of look into a more detailed version of this. So first of all, I have this financial data which I'm going to show. And let me just plot it like before. So very simple. In the Quantile Regression mode QMon, I can actually specify what I want to do, dateless plots. I can say, instead of me, dragging all this, let me do something bigger here. I can specify one option. I want this bigger data. All right, and now I want to do more or less the steps which I did here, right? And the idea is that some of these points, when I do my fitting, some of these points, they're going to be seen as outliers. So let me just repeat more or less the same thing I did in the previous pipeline. So I'm starting here, though, we can see that we have much more points. I'm going to start with, say, 100 nodes. Again, I'm doing this at 0.5. And let me see what is the result. The result is good, but before plotting, let's actually do something like set regression function options, which I want to be this. And this is, I forgot to put the monadic pipeline. All right. A little segue here. Monadic pipeline symbol. I'm using escape equal sign greater escape, and I produce this line, right? You can enter it in this way, but I have, and also this is a symbol in Mathematica. If you do say full form, I'm not sure is it going to do on this. It's going to work on this directly. Well, it didn't, but this is basically double long right arrow. So if I do something like that, you can see that this is the symbol. I mean, this is another way to enter that symbol, right? Basically I copy and pasted that, and immediately was front-end interpreted as such. I'm using a shortcut. I programmed a shortcut in my front-end, which with combination of keys, I produce immediately this kind of pipeline. This can be important, but I'm not sure I discussed this before in the previous session. All right, back to the pipeline. So we have fitted this. We made the Quantile regression, and so here we want to see the points which are like potential outliers. And so again, I'm going to plot the errors. And let's see what is going to happen. All right, so yeah, I mean, find some of these. This by default, this function uses relative errors. So I'm going to put relative errors to relative. I'm going to put relative errors to false. And now from here, I can be conjecturing which are the outliers. I mean, I can see what points which have which are like, say, like far away with distance 2 from the fitted curve, the one in red, would be considered outliers. I actually I actually packaged this in a function, and I'm just kind of going to copy and paste this whole thing here, right? And so so in this function, what we get is I assign the whole thing to an object, and this object 2. If I take the value, again, we're getting out of the monad. If I take the value, these are presumably the outlier points, and I can plot all together what is the original data, financial data, and the found outliers. So this is Q object 2. And I mean, we can see that the points which are picked by in this way were considered outliers. Well, can I do something better? Actually, I'm sorry. I slightly misled you here. I need to use a threshold here, and I'm going to use a threshold which we saw in the previous run to be 2, right? So again, let me do this again, right? So from the errors plot, I'm seeing that points above 2, the outliers. And so here, I mean, we don't have drastically different result, but this is a different, this is the approach I'm discussing. This is the approach which we saw here with cleaning the data. We're fitting a curve, and we're looking at the errors, and we're picking visually a threshold here from the errors. And I'm using this threshold here. I have specified to be 2, and I'm extracting the points. Now, an interesting another approach of this, and let me put this into, say, using thresholds, right? Another way to do this is to actually use outlier identifiers. And what do I mean by this? So there's a package I wrote some time ago for doing one-dimensional outlier identification. So here I'm going to do, say, outlier identifier. I'm going to do, let's actually put, let's use this sample data points, right? And so here, this actually needs to be specified what identifier I'm going to be using. And in this particular case, because this is a one-dimensional identifier function, I need to do say that I want these points. Now, this probably is not going to detect any outliers. Well, it did, but the crux of this is that the point itself is not considered an outlier given this. So the outliers found were actually some of these other points. I'm just using opportunistically this data as an example. If I do this with the financial data, right? I mean, I can find outliers. I can do, there's a different outlier finder, which is much more conservative. And there's another one called Quantile. Which it's kind of in between. Both of this, say, if I go back to the Hampel identifier, I can actually prefix this with, say, something called top outliers. And this is going to produce only is going to give only the outliers which are like large. I mean, if we look at this data, right? If I look at the summary of this data, we can see that the points which are being picked, they're obviously into this larger part. If I would say something like bottom outliers, then I'm going to get points which are on the low end. All right. So now this, as I said, is the different approach of finding outliers, and this is when I copied and pasted the pipeline earlier. This is what is happening here. I'm actually saying that for our financial data, after we fit the curve, and let me modify this again to be with red. Style. When I'm doing this, and when I'm trying to plotting the points together, I did actually, I use this more conservative outlier identifier function. If I change this to Hampel, again, this is going to produce different set of points. Much more points. All right, so these are the two ways to find point anomalies based on residuals, because we're approximating the signal with some curve. We're looking at the residuals. I could have tried to make a bigger fit, like with more nodes here. Presumably some of this is going to change. Let me try this right now. And then by changing the interpolation order, changing the number of nodes, or specifying the actual nodes, we'll presumably be getting different results also by changing the identifiers. But at some point, I guess we need to declare victory and decide which one was a good produced good results and satisfactory results. I do in this particular case. I would rather be doing the S plus. All right, now here I saved an example from Mathematica's help browser, in which there's some similar kind of activities, point anomalies are being found. What is happening here? This is like although we're looking into point anomalies, it's kind of like using contextual methodology, and I'm going to explain. You see how the financial data was partitioned in this overlapping windows. So if we look into this, say the first 6 of those, right? You can see this point. Sorry. Actually, let me do column form. Right. We should be able to see that there's some correspondence of this overlap. You see how the first one corresponds to this one, and so forth. So, okay, so we have this overlapping partition, and then we're just putting this to find anomalies. Find anomalies looks at this as a bunch of vectors, bunch of points in a 4-dimensional space, and it's trying to find, the anomalies in that particular kind of space, and the anomalous sequences of 4 are being essentially plotted here. Yes, there should be some agreement with what I considering, like say here, you see this kind of point, and this point, actually, let me turn this into a dateless plot, right? And fortunately, I need to say also a joint to say that I don't want to be joint, right? I'm not sure is this true and false. I'm not sure is this going to work. Well, it did work. Okay, and so when we see, and I guess I'm using here some aspect ratio. All right, so I'm going to do that too. Now we're in a better position, I guess, to make visual comparison. And probably I should have used detailed plots, right? Like plot theme, detailed, and etc. But I mean, we can see, but basically there's some agreement by the points I'm finding with my method and the points found with this method. They're quite different though. And it seems, I'm not exactly sure what fine anomalies is doing, probably it's using some neural networks and etc. But this is a different, this approach, it's based on quantile regression. This also goes back to what I was discussing in the previous talk, but there's some analogies, a strong analogy between what quantile regression is doing and its computing and etc. and neural networks. The different algorithms, well, both rely on optimization. They're different algorithms, but you know, we have a basis of functions and we feed them and we do stuff with them and so forth. All right, so I'm going to go to the contextual outliers, which is something happened here. Which is somewhat easier and more direct to discuss. So, okay, this really, it's not what I expect. Okay, yeah. All right, this time I'm going to use not financial data, I'm going to use temperature data. So, as I said, I had this temperature data from Orlando. I'm going to use that data. And here I'm going to also echo the data summary, and then I'm going to do the plot of the data. Actually, let's do a data list plot. And I can be, because I know what is going to be happening, I'm going to put image size large. All right, so yeah, these are temperature points. Actually, let's do something more here. We can do plot theme.
Anton, can you also comment on the difference between column 1 and column 2 on the data summary?
Okay. Yes, I used this before. Okay, this is one of the missing functionalities in Mathematica, to make quickly summaries of data. And so record summary, there's this package, Mathematica for prediction. You can see it in the completion here, Mathematica for prediction utilities. And so if I do, like, say, this sample data, right, or whatever, or any kind of data, it's going to provide this breakdown. I can probably, I think here I can say regressor, right, and then value. And this is going to label what is what, right? So here internally, this package QMon is using that Mathematica for prediction utilities package. So the record summary is done for that. If you, so what you're seeing here, right? It's exactly what is being done. It's being called, TS data is a time series. So I need to actually take the path of the time series, and it's not just that simple. Yeah, right. Now these are also, you see, they're not treated now as numerical values. They're treated as categorical variables, and so that's why we see that. And but this is also useful. We can see that the temperature 26.78 degrees Celsius has happened 22 times. So, all right. Well, this is used internally. The quantile regression, I'm going to opportunistically use this. The quantile regression package strips this, it uses time series as they are. You see, TS data is a time series object, right? But if I do say, go into the monad, so basically just uplifting the data into the monad, and then I immediately get out of the monad by with take data, right? This is no longer a time series. This is just the path, the way I was expecting this to happen, the path without the units, without the quantity being wrapped. And now with this, this summary here, what you see is corresponds to what we see here in the table. I can do this further and say time and temperature. And yeah, so hopefully this answers the question. And yes, that's actually a good, I mean, it's a good summary of some of the other functionalities. And because I'm going to share this notebook, I'm not going to delete everything I just typed in. All right, so back to this one. So what is so here we want to find outliers. So this is the way I find contextual anomalies. So with the outliers, let me do here some Quantile regression and say first of all, let me just do it as this, right? Just to see, do I have a good fit? And it seems to be adequate, right? The fit here, I mean, it's not overfitted, but it's not also underfitted. Now, what I'm going to do in order to find outliers, I'm going to do say, I will consider anything which is say above below 0.2% and everything which is above 98% to be an outlier. So here, so this is the curve already. And now when I say find outliers, I think I can directly just plot the outliers in this particular case, right? So, and since I'm plotting the outliers, I'm going to do all this into the copy and paste all the options, and I'm going to say that I want this to be a list plot. And yeah, well, obviously, if I put detailed, then some other things happen under the hood. But okay, without detailed, then we basically just see the outliers. And all right, so in this, so this is how we proceeded. I'm going to assign this to another object. I'm going to call it QAmon Q object not 2 but 3, right? And ideally, I want to say, for whatever reasons, I want to take the outliers after I have made the plot and to do something with them. For this though, because when I plot the outliers, the last value, usually the last computation in the pipeline is going to be the value of the pipeline. And that's why I'm actually going to recompute the outliers. I don't want to do the outliers plot. I just want to recompute the outliers. Actually, I think the outliers, I apparently forgetting about this package. The outliers are also first class citizens, so to speak. So if I can, I didn't need to do what I just did. I can just take the outliers. Yeah, I can just take the outliers. All right. So sorry. Yeah, this would have worked. I could have taken just the value, but there's no need for it. So here, the outliers, when this plot is made, in the context of the monad, the outliers are being saved. So if I look into this, if I look into the monad is basically having two things. It's having a context and a value. And so if I say something like QAmon take context, right? This I can show you the keys because the context is an association. And you can see we have the data, the regression functions, the outliers, and the outlier regression functions. The outlier regression functions, they're put here in gray. They're the ones which we use to find the outliers. When I say QAmon take outliers, it's just invoking this. It's just picking this element here. If I set Q object free and then QAmon take value, this should be a plot because this is the last thing we did when we executed the pipeline, right? So the pipeline values of the monad, it's a heterogeneous kind of element. It can be anything. It can be number, it can be plots, it can be some other things. So in some other situations, so basically further, if we want to do certain further investigations, we can pick the outliers in this way. And, you know, we're being separated into top outliers and bottom outliers. I do. There's another thing to consider, and I actually showed you already the packaged. Let me contract this, and I went much further ahead than I thought with the presentation. So let's actually look into some other type of anomalies, and so this is structural breaks. So again, I'm going to use the financial data because I would say that's actually a very representative and interesting example for structural breaks in general. Financial data provides such. And so here with the quantile regression, actually I don't need to do a quantile regression. I just wanted to do echo data summary, and I wanted to do a plot, right? Okay, great. So with this one, I'm going to make another object. Let's say object 3. Object 3 is taken, object 4. And let me do out of the box. This should be, come on, find. Well, I guess I did not load that package for the structural breaks. Let me see. Find show test maxima, find anomalies, and the. Okay, well, I might give up here. Apparently, the package I wanted to use for this is not being loaded. I'm going to try to make one more attempt of figuring out how to use it. And okay. I guess this is the show test. Show test is there's a show test statistic, and there's a show test maximums, and I am going to just do something from a separate study and see what is going to happen. And here I'm going to do all right. So this is a little bit of a more complicated example, which shows a couple of things. So in this time series, we can see that why we're looking into this and why we're using this structural breaks and etc. Right? So the ones which are being found, and let's kind of look into these points here, 2014, between 2015, 2016, a little bit after that, right? So if I put this into a dateless plot, and actually bravely here, I can do plot, I can do a plot theme detailed, and I want a large image. So if I try to do, say, linear regression only on this fragment of the time series, I'm going to have a line. But then on the next fragment, the line is going to be different. And then we're going to have this, and then we're going to have this. So to some extent, this is what these points are being, we're finding here. We're actually, from what I see here in this plot, I see the identification of where the structural breaks are. And you can see that this red line corresponds to this plot here. And I'm going to try to convince you in a better way about this. So I'm going to take one graphic here. And in this quantile regression object, I'm going to take the value, which is a graph. And so here in this plot, unfortunately, what I see is, all right, so I'm going to take the points. So show test points or ST points. And I'm going to do QMon take value. All right, and now I'm going to do show of the graphic I did earlier. And what was the graphic? GA1 and a list plot of financial data together with so the graphic I'm doing, probably it's redundant. I can just do this, and I can do, say, grid lines. And from the grid lines, I can take the points which are bank here. So this is the structural points on the first coordinate. Okay. Now, what this is telling us? It's that if we try to fit, if we try to do, say, linear regression with simple lines, these points here will produce different regression. And you can see, if you consider the fragment of the data just from here on, right, and you do linear regression with this is going to be different from the linear regression, which is going to be just for the left side of this middle line. And similarly here, we're going to have a regression line which goes in that direction, and then here we're going to have something else. So I'm going to demonstrate this with a plot for the next 5-10 minutes. And so this here, it's the quantile regression. I'm going to pick the points which I have from the financial data to be in such a way that the regression is being done with the points only from the points which have time less than this one here. So I'm going to do a selection of the points, and here less than equal, I guess, then the 0.11. And here I'm going to do a fit with linear regression, which is with the functions 1 and x. And then I'm going to plot the whole thing. Again, let's do this to be large. All right, something is missing here, some syntax. All right, so yeah, we just fit a line through this here. All right, so and I want to compare the two plots. So what I'm going to do is I'm going to take this as a separate plot, and this is, say, plot 1. All right, and now I'm going to do exactly the same thing, but on the other side, right? So, and now I'll try to do both plots together. And in order to do that, apparently, I need to increase the plot range. So we'll do that when we're imposing this these two plots. I need to make sure that the first plot and the second plot have the same, can be placed in the same background, the same of the plot. So I'm going to take financial data 1, and here it's this, right? Ideally, this should work. And now, apparently, I obviously need to do this on the other side too. And so, sorry, min max. And that's for the y values. Okay. Now we're in game. All right. So what we can see, I mean, these two lines, in blue, right? It's almost unnoticeable, the first one. And this one, this is a structural break. I mean, there is no, if it wasn't a structural break, this would have been a straight line. If I repeat the same thing, if I repeat it, say, for the middle point, right, which was here for both, and so, and we can see, we can also see clearly what this is a structural break. So structural breaks, they're another type of anomalies. And this has been packaged into the quantile regression monad to a point. I mean, to a fairly advanced point, except the plots. The biggest thing to which on which this methodology of finding structural points relies on, it's actually the ability to find local extrema in noisy data. And this is the last thing I'm going to show. And so it is related to this structural breaks finding. So so if I look into, I think the Orlando data is better to illustrate this. So I'm going to do the Orlando data. And so here I'm going to do quantile regression with say 12 nodes, and I'm going to do, I need to fit more or less the same type of probabilities, need to use the same type of probabilities which I used for finding outliers, very close to the 2, 0, and 1 respectively. So I'm going to plot this, but then the local extrema, in order to be found, I need to do equal. So we're still in the monad here. I'm going to assign this to an object because I'm entirely sure I'm going to do something else related to this. All right. So this here, what is exactly happening here, right? I mean, you can see that if we're around this point, it is not exactly clear what is the local extrema. Is it this one? Is it this one? Right? Same here. And I mean, I can probably change. This is not going to change the results drastically, but the local extrema, the way it is found here, it is in that way. So let's actually plot this. So what I'm going to do is I'm going to do a dateless plot again with the temperature data. And here, what I'm going to do is, let me think a little bit. I need to combine the two plots with a list plot. And I need to tweak the plot style first here. Let's do this to be gray. And the list plot is going to be this fifth object. Again, I'm going to get out of the monad and take the value. Right. And I'm not exactly sure what this plot is going to do with the association. So just to be safe, I'm going to do this. And let's see what is going to happen. All right. So now this this part here was not picked, but say I would like it to be picked. If I go here to this plot, right, we see that most of these maximas were found, and to some extent it might be not particularly obvious why I'm using this at all. I mean, isn't just I find the maximum values and this is my local extrema. Well, yes and no. It's not necessarily the case, but I'm going to try to tweak the computations here in order to be clear what exactly is going to be happening. So if I do with the local extrema, what exactly I'm going to produce with how I can tweak the elements in order to find the points I want. So find local extrema takes two options. This the nearest with outliers. That's it's using the function nearest, and yes, it's using outliers. I'm not by default is false, but I'm going to try this to be true. The other one is the number of proximity points. Which by default is a relatively small number. So let me just increase it. I misspelled it. All right, so this produced somewhat better result, at least in principle. We did get the point I was referring to here. And let me do this again here with a larger image size. So what I was saying, but I want this point to be picked. We can see what this point, it is being picked. If I want to make some plot here closer to what it is above, I'm going to do joint false, right? And yeah, this is illustrating what is going on. So let me put this to false and see, am I going to produce better results? And yeah, well, okay, we need to experiment with this. I mean, obviously, asking for more points, it might produce somewhat, the results would be different. Yeah, we see what now we get this. And, arguably, these local extrema are better. So, all right. Now, this is, by the way, a fairly unique implementation of quantile regression application in Mathematica, because it uses, after the curves are being fitted here, right? If I look into this object, a quantile regression object, if I take if I get out of the monad and I take the regression quantiles, this is the curves, right? So these curves, I mean, you can see here, they have some expression. Maybe I can, let me see if I do this assignment and I do say, this is an association of functions, and I can try to do simplify over Q funcs, and then each of them is applied to a symbol. Okay. You can see how these functions, they basically, with the piecewise, they are polynomials. I can differentiate these polynomials, find the actual extrema. I can find the extremas here, the local minima, the local maxima. Because I fitted 2 points, if I have fitted here 1, I can still probably use that to a point. I'm not sure how good result is going to be, but I'm still being, this is still, this fit here. I can use both the local minima and the local maxima in order to find the points. And so I'm differentiating, then I'm using nearest, which this function, this option hints to. And with nearest, I'm finding the points which are the closest to the found theoretical extrema. Now, this here, what is happening? There's a structural breaks test, going back to the structural breaks identification. There's a structural break test called the Chow test. The Chow test is systematically applied over the whole, all of the time series with a certain step. And then on these results of the Chow test, I'm actually finding the local extrema. These red lines, they're indicating where the local extrema is. And then, this is how the functions have been produced. All right, so in summary, I'm ready to.
Yeah, we only have a few minutes, yeah.
Yeah, in summary, right, we look into 3 types of anomalies. One of them was point anomalies, and we found them in 2 different ways. We have contextual anomalies, which actually in Mathematica implementation here uses contextual anomalies in some sense, but we can use contextual anomalies through outliers identification. And then we look into structural breaks, which they're anomalies, but they're more like theoretical construction anomalies. And yes, they can be important, especially if we're doing certain type of analysis for time series. Well, thank you for your attention, and if any questions or.
Thank you, Anton. Let me check. Since there's no question, I guess, we could wrap up our session. You are watching the second live coding session with Anton Antonov. You can find a recorded video on Wolfram Research YouTube channel. You can interact directly with Anton through Wolfram community. Thanks for watching and have a good one.
Yeah, thank you, Matt. Thank you all.